To get started, my name is Sally Jewell. It's my privilege to introduce our speakers to you tonight. I am on the Board of Regents at this wonderful institution, the University of Washington, but more important, tonight I'm here as a graduate of the College of Engineering and a proud ME alum. So it's my pleasure, along with my husband, Warren Jewell, to support the College of Engineering and particularly the Department of Mechanical Engineering, where we graduated. We also have a deep interest in this topic because after graduating from here, we both went to work for Mobil Oil as petroleum engineers. So as we watched the disaster unfold that started on April 20th in the blowout of the Deepwater Horizon oil rig, we had a lot of dinnertime conversations about what's going on and how could this happen, and who's responsible and what's really flowing down there. And clearly, that was an interest that many of us took in this particular situation. And of course, those most interested are those responsible for overseeing oil and gas in this country and the resources, and that's the federal government. So during that time, the government was very, very interested in figuring out what's exactly happening and what can be done to stop it. And one of the critical questions that they needed answered was, what's the flow coming out of that well? How much is entering our environment so that they could put plans together to mitigate that? So in May, the month following the explosion, our presenters, Professors Jim Riley and Alberto Aliseda, received a call to participate on a national task force of scientific experts to estimate the flow from the spill. And I'm sure many of us remember that discussion unfolding in the media. Both of them are expert fluid dynamicists. Jim holds a Paccar professorship and is a pioneer in the development and application of direct numerical simulation to flows of various types of liquids. Alberto is an expert on the dynamics of multi-phase flows, such as bubbles in water and droplets in air, or as we were talking before the presentation tonight, blood, clouds, tidal flows, and all manner of things, not oil and gas, actually, in their day-to-day work. But they both said yes to participating on this national task force, and their lives quickly changed. So tonight, we're going to hear from both Jim and Alberto about their work and their experiences on this task force. Jim is going to begin the presentation this evening, so please join me in welcoming Professor Jim Riley. Jim?
Hey, thanks, Sally, for the kind introduction, and also thanks to you and Warren for what you've done for the department as well. And I guess to Matt O'Donnell and his staff for helping in all of this, for inviting us and giving us a lot of help. So Alberto and I are going to talk about or discuss some work that we've done in estimating the rate that oil was flowing into the Gulf of Mexico in the BP oil spill or from the Macondo well. And as Sally said, I'm going to go first and give more of the background, and then Alberto is going to talk about the techniques used to do the actual estimates. But before I do, maybe bring up a couple things that Sally mentioned. So our backgrounds are mainly in fluid mechanics, and so we deal a lot with flow. And so as she mentioned, you think of a lot of problems with blood flow. There was some talk about energy here, where we do combustion as well, try to improve combustion devices, flow of various chemical species and reactants and products. We're also doing some work on the Puget Sound, the flow-through turbines that might be capturing some of the tidal energy in the sound, and a lot of other things. And also, we deal with problems on different scales. So we've analyzed flows at the microscale, say a device that's maybe a couple of millimeters in size, one that you'd have to use a microscope to even see the flow, up to we've worked on the behavior of certain types of stars that are expelling mass, planetary nebula. So very, very different scales. But up till now, we haven't ventured into the oil business, and so we got into that. But I bring up these points not to kind of glamorize fluid mechanics, but maybe, but to mention two things. One is that the physics of all of these problems are very similar. Each one problem has a different twist. One might be turbulent, one laminar, one might be compressible or not, but the basic equations even are almost the same. So the topic spreads across a lot of fields. And also, what's important, what we'll talk about tonight, is that the methods, especially the imaging methods that have been developed in the lab over the last 10 to 20 years, used mainly in the laboratory, are available for a lot of other problems, and that's what we're doing here, we'll talk about tonight. So anyway, given that, to kind of orient you, so this is the kind of northern part of the Gulf of Mexico, and the BP site is right there. It's about 41 miles, to give you an idea of the scale, it's about 41 miles to the nearest land point. And the site's called the Macondo Prospect. It was an exploration site, not an existing well. And you can see some of the geographic areas. There's New Orleans and Lake Pontchartrain and Mobile Bay and Mobile and over to Florida, over to Port Arthur. So that's the area. Now you can see it, you can get a little bit better idea of this by looking at the bathymetry of the Gulf. And so the bathymetry shows like the deeper sections of the Gulf right here, and then the areas near shore, the continental shelf areas here, and these little red dots are all oil wells. And you can see there's none in Florida. You come around here into Mississippi and Louisiana, and you start to see a lot on into Texas. So most of them are on the shelf. But you can see in Texas, some of them are starting to be going into deeper water, somewhat deeper water. But the BP site, this Macondo well, was right here in a fairly steep escarpment. So it's much steeper here than in this other part of the shelf. And it was located about a mile deep. So the well site itself was about a mile down. And to do the exploration, and you may have seen this, so they used a rig called the Deepwater Horizon. It's an offshore drilling rig that's semi-submersible, and it's also can move under its own power. To get an idea of the size of this, it's about 112 meters wide, so it's wider than a football field. Its draft is about 23 meters, and then the total height of the thing is about 97 meters. So, and when it's in full operation, there can be up to about 130 people on the rig itself. And one of the things you can see in the photograph is this pipe coming out, and that's the riser, and that's kind of a key part of what we'll talk about. So over on the right here is a cartoon that kind of gives you an idea of how the whole thing was set up. Here's the Deepwater Horizon sitting on the top surface floating there. And on the ocean floor is a blowout preventer, which was supposed to do what the name says. If there's a blowout, it's supposed to shut everything down. It's one of the things that didn't work. And then connected to the blowout preventer was the riser. It's about a 21-inch pipe. It doesn't show it there, but it's about a mile long. So it's a good bit of piping. And then below it then is the well itself, the piping all the way down to the reservoir, the oil and gas reservoir down here. And that goes down about several miles. So it's a mile down to the ocean floor and then several miles down to the reservoir. So it takes a lot of technology to explore this and to deal with it. The whole flow is driven by pressure. So the pressure down at the reservoir is really high. It's over 11,000 pounds per square inch, compared to atmospheric pressure up here is about 14. So it's almost 1,000 times the pressure, atmospheric pressure. And that will drive the oil and gases up the pipe. It's got to work both against gravity and then against all the losses in the pipe as well to get it to the top. And right below the blowout preventer, it's estimated the pressure was about 3,500 psi. At the ocean floor, it's about 2,250. So there's a lot of pressure drop there to drive the flow through the blowout preventer and the piping and all. So that's the setup. And I think, as everybody knows, then on April 20th, there was a big explosion. And it was the evening of April 20th, explosion occurred, and then there were multiple explosions. And in fact, 11 of the crew were killed, 11 out of the 126 that were on the rig at the time. So it blew out, and the fire started, and the fire was probably fed by the hydrocarbons that were coming up the riser, because the fire burned for about 36 hours. It just continually burned. They couldn't put it out. And finally, the rig filled with enough water and it just sunk to the bottom of the ocean. And as it sunk, the riser went down with it. So it sunk on April 22nd, and this vehicle is down to the bottom plus the riser. And so BP went down then and started to explore what was going on there. And this is what they found after a couple days. So this is their sketch of the riser here. And here's the wellhead right here where the BOP is. And here's the end of the riser. And they found, after a couple days using these remote operated vehicles, these ROVs, that there was a lot of oil coming out here at the top of the BOP, and then a lot of coming out at the end of the riser as well. And so you've probably seen, so this is kind of a cartoon of what it looked like then. So here's the ocean floor, the blowout preventer, and then this riser just bent over when the thing fell. And so there was a kink here and a lot of cracks in the kink, and so the oil and gas was coming out of that. And then this was supposed to be a mile long, and then oil was gushing out of the end here as well. And these are things that you probably saw on CNN website or various other places. This is just a frame here from one of the films. And you can, on this side, this is the flow coming out of the riser, out of the end of the riser, just pouring out. And then to the right is a frame from the film. And here the riser, it's at the top of the blowout preventer, and the riser is fallen away from you. And so you can see there's several cracks there, and oil is kind of gushing out of that as well. And the amount coming out of that was not unappreciable. So our objective was to try to use films of this stuff to make the best estimates that we could of what the flow rates were. Now, a little bit later on, and I'll mention the time, what BP was trying all these different ways of shutting the thing down. And later on, what they did was they cut the riser off and just laid it on the ocean floor. And then the oil started gushing right out of the top of the BOP, at least for a couple days until they put a cap on that. So it took them a couple days to cut the riser. This is right on top of the BOP. When they finally got that cut off, then there was a flow coming up like this, and we had some videos of that as well. So we had kind of two different times where we can make measurements of what was coming out. So, okay, so now the question comes up is and maybe this is pretty obvious to most people, but why would anyone want to make flow rate estimates? And the first reason is to help in dealing with the response to the overall spill. Like how many ships do they need at the surface, how many skimmers do they need, and all these other things dealing with the response. What the government didn't work so much on what we estimated, but they worked on worst case scenarios. And so actually before the accident occurred, BP had estimated that if the whole riser was removed, that about 160,000 barrels per oil per day would be coming out. Later on, after the accident occurred and the riser and the BOP stayed on, the blowout preventer was still there, they estimated the worst case of 100,000. And those were numbers that the government used to deploy their ships and everything. On the other hand, I think it's pretty clear that estimating the short and long-term environmental impact, in estimating that, you really have to know how much oil came out. And in fact, that's where a lot of the research is going on now, that people have some idea of how much, they know what came to the surface. They have estimates of how much was burned off and how much evaporated and how much was skimmed and stuff. They need good estimates of how much was not at the surface. And that's one of the main reasons to make estimates. And so you see now there's a lot of field experiments going on and looking at underwater plumes and how fast they degrade, how it affects oxygen in the ocean and sea life and all. So the environmental issue was important. Also, there were obvious political repercussions because the administration was being heavily criticized for kind of a slow overall response. And whether that was justified or not, they were very sensitive about that issue. And so they wanted to get the best estimates they could all the time and show that they were on top of it. But a fourth issue was legal. And I think, as you know, almost immediately after the accident, lawsuits were starting to be initiated, from the fishing industry and from the travel industry, and you can kind of go on and on. The states were planning lawsuits, some of the local districts, counties, and the national government. A lot of lawsuits were planned and are being followed. Now, a lot of the lawsuits are based on the amount of oil spilled. That becomes important, how much was spilled. And just to give one example, the Clean Water Act, under the Clean Water Act, the U.S. can seek civil penalties of from $1,100 to $4,300 per barrel of oil spilled. And we'll find later on that if you take the final estimate of how much was spilled into the Gulf, multiply that by the worst case, the 4,300, you get almost $20 billion. So, I mean, the numbers are just fantastically high, and that's only for this one civil suit. And in fact, it means that if you make a 1% error in the estimate, that's about $200 million difference. So they're numbers that people aren't normally even used to thinking about. But so the legal issues are really big. So there was interest in making estimates, and on the day that it sank, the Coast Guard made an estimate of about 8,000 barrels per day. A barrel is 42 gallons, so this is something like 330,000 barrels per day. It's a lot. Seems like a lot. But their estimate was based upon the amount that was in the vessel itself. There was about 700,000 gallons of diesel oil in the vessel. So that was their early estimate. Now, the first day they took the probe down after the rig sank, they couldn't find any trace of oil, and they thought maybe this is going to be okay. But they kept looking around, and then the second day they found these two sources. And probably in the understatement of the day, Coast Guard Rear Admiral Mary Landry said they have a serious problem. Actually, at the time, the talk was more about the people that were killed and their families and about the people injured. But now people started to think, well, maybe this is a serious oil spill. And at that time, the Coast Guard and BP together estimated about 1,000 barrels per day. So that was kind of a first estimate. Now, a few days later, just a few days after the spill, NOAA, that's really NOAA in Seattle, that has a lot of responsibility for oil spills, they made a kind of a quick estimate, and they said 5,000. Although their numbers in the report that you read they said up to 10,000 or possibly more, but the press picked up on the number 5,000. And so that's what people were talking about for the next couple weeks. The government says 5,000. But is it really 5,000? So when you start looking at the problem, watching the news and stuff, you really get the feeling that there's substantially more oil than 5,000 barrels per day. So this is kind of give you an idea of it. This is the fishery closure boundary on May 11th. So this is a couple weeks later, and that's the red lines. And if you watch that over time, you just see that expanding to a large part of the Gulf. Or if you start looking at the Gulf from satellites, this is from the Earth observing satellite called Terra on April 29th. So this was just a week after the spill, and you can see that it's already occupying, a fairly significant region. And when here's Florida over past New Orleans, and so that's growing. And then this was done by Sky Truth, an environmental group, and the resolution of the image was very good. And so when you blow this up, show this little area here, you see that already the slick is starting to hit land there. And they made an estimate, but again, their estimate was just based upon what they could see at the surface, and it was about 20,000. So So there, all these numbers were coming out. I failed to estimate failed to say that the NOAA estimate of 5,000 was just based upon what they could see at the surface. NOAA was much more used to making estimates of much shallower spills. So, and then you could, with satellites, you could just watch that grow. Here's a couple weeks later, and it's occupying a lot more of the Gulf. So, and just a lot was going on over that time. There was controlled burning of oil on the surface. You know, there was water, there was oil and tar coming into the beaches, and so all of this was being reported in the news a lot. And there were estimates from the 5,000 up into the 150 to 200,000 and everything in between. The trouble was that there was very little hard evidence. All they could do was see the surface, and this thing was happening a mile down, and so there just wasn't good information on what was subsurface. But the game changer occurred on May 12th, when, for some reason that we don't understand, BP released a video of the flow coming out of the riser. And so that, within the next day, that was shown on PBS News, and it was put on YouTube, of course. And so now everybody is starting to have access to this. And when you watch it, it's pretty dramatic. And in particular, when a fluid dynamicist watches it, I mean, there's many people around the country that know how to work with images and use them at least to make estimates of the flow. And it turns out that same day, when I look back at my emails and stuff, that's the day that we got into it, that Bill Lair from NOAA in Seattle called me up and asked if I'd want to be involved. So fluid dynamicists started looking at this, and by the way, on the 13th, BP said that you couldn't use the video to make any estimates. It just wasn't possible. So the next day, a colleague, Steve Worley at Purdue, was interviewed on NPR, and he had taken the films, used kind of the methodology that Alberto will talk about. Now, there's some problems in what he did, but he was getting 70,000, and it was clear that it was much higher than 5,000. So that kind of broke the ice in a way. And so that day, then I knew that Alberto had worked on this. He had used imaging and stuff before, and he was used to the technology. So I talked to him and asked him to join me. And then we really needed help. And so Oscar Flores, who's a postdoc working with me, but on a very different problem, said he would join as well. So there was 3 of us. And so we realized this was kind of going to be a frantic month. And the trouble was that this was right in the middle of an academic quarter. So we're teaching, doing research, you know, and in fact, I had a trip planned to National Center for Atmospheric Research to give a talk and talk to people there. And then I had another trip planned at the end of the quarter to go with some undergraduate students down to Johnson Space Flight Center, where they were going to do some tests on a microgravity airplane. So we had a lot of other things on the table, and Alberto had 2 trips to national meetings with graduate students and stuff. So we had, you know, more than a full plate of stuff to do, and we realized this was going to keep us busy. And if we did it, this was going to be weekends and nights and all of that. But we decided it sounded interesting and important, so we decided to go ahead. So I'll tell you about getting into it in a minute. I thought it was useful to kind of describe the structure that developed in the government in doing the response. And so ultimately, Steve Chu, the Secretary of Energy, kind of nominally came in charge of estimating the flow rates, I think kind of on a volunteer basis. But the person running the overall show and running the response was Thad Allen, who was probably the most visible. So people probably saw him on TV and in the news a lot. He was previously he was a retired Coast Guard admiral, and here he was a commander of the National Incident Management System, which is part of FEMA. And so he was in charge of the overall response to the spill, and of course estimating the flow rate was part of that. And so what Allen did was ask Marcia McNutt to be, you know, head of the flow rate group. She was the director of the U.S. Geological Survey, which is part of the Department of the Interior, which is the one that does the leasing of these wells and stuff. So they're heavily involved in the oil business. And so a flow rate technical group was formed and under Marcia, and there were 3 teams. The plume modeling team, which was us and some other academicians, one of them, Steve Worley, the person I mentioned, a couple people from government labs. And we were mainly using videos and this particle image velocimetry that Alberto will talk about. There was also a mass balance team that was kind of using the older methods, using airborne and remote sensing and estimating how much was burning off, how much was evaporating, and how much was skimmed up. The trouble was that they didn't know anything about what was subsurface, and so they could only tell you what was happening on the surface, which could be useful because then if you subtract that out, you might get a better idea of what's below the surface. And then there was another team that was doing reservoir modeling, kind of standard petroleum engineering, where they were estimating flow rates from the reservoir up to the wellhead. So there were these different groups. And so we started working on May 14th. And the trouble was we had really sketchy information. Even the riser diameter itself, it was all bent up. And then there's a pipe inside the riser, and there's cables down the riser. All that geometry wasn't clear. The gas-to-oil ratio turned out to be a problem the whole time. We were getting good estimates of that, and that was a key parameter. Also, we couldn't get any films, so we had these YouTube videos, which are nice to watch the thing, but we really need high-resolution films to do what we want to do. So we got things running, and then on the night, and we kept asking BP, we need better films. So on the 19th, we finally got some films from BP, but they were YouTube quality also. So we had this kind of not really good films. And then we also joined with, it's kind of a long story, but we joined with Juan Lasheras from University of California, San Diego. So there was a team of 4 of us. And Juan was using similar methodology, but different codes. So it was a good way to check each other's calculations and just good interaction and stuff as well. But we were told, that was like a Wednesday, and we were told by Friday that the government needed a number. And so we had this poor video and sketchy information. And so we started doing what we could. And then we had a teleconference on Saturday. There was our team members, this plume team, plus a number of people from the government, and we haven't figured out who they all were. There were all these names in the beginning, and they introduced themselves, and then that was it. But they were from key agencies, and then there was at least one representative from the White House, and then there was a person from BP, who, as you might expect, wasn't really popular in the meeting. But it turned out that he was really useful because we could tell him what we needed, like better quality films. We also needed good information on the video cameras, like frame rates and things like that, in order to use them. So he said that he would go off and do that. That was a Saturday. Then we met again the next day and discussed this more. And that's the time that Marcia became head of the overall effort. But we couldn't say much. We had these poor quality films and sketchy information. And so all we could say at the time was that we felt it was at least several times larger than 5,000, but we couldn't make any harder statement than that. But we started to get better videos, at least. These were of the flow coming out of the end of the riser. We weren't getting good videos or videos at all of the ones in the kink. And so Alberto and I had a chance to see Bill Air at NOAA, which was really interesting to see their setup and everything that was going on and where they were going to be bringing the films and stuff. But then we had another teleconference with our team. In fact, we were having 1 or 2 per week then as things developed. And so based upon pretty sketchy information, I think we had one good quality film in of maybe a half an hour or something. I can't remember how long it was. So the first thing we said was, based upon the information we have, it's probably kind of on the lower side between 12 and 25,000, but we said it could be significantly larger, and that was what was in this report. So we sent that off to Department of Interior, And they issued a press release where they took into account the other estimates. Well, the mass balance team was just looking at the surface, and their estimate was 12 to 19. And the statement that the Department of Interior put out at the time was 12 to 19. And so the press picked up on the number of 19,000. So it went from 5 to 19,000 in the press, and people were talking, and that's what people were talking about. So the thing that happened, though, was when the Department of Interior issued the press release, our names were on it. And so we immediately started getting contacts by all of the local press, national, and even some international press, and it just kind of continued. But we were getting better videos, kind of gradually. They were getting better. So BP kept at it. You probably heard of the top kill and all kinds of other things that they were doing. And it was on the second and third, it took them 2 days to cut the riser away from the BOP, or from the blowout preventer, and that gave us new videos to work with. So it gave us a different way of making an estimate. Although we didn't get good videos for a while on that. So we had another conference to look at some of the other videos and at least kind of YouTube quality videos from the cutout part over the blowout preventer. And then there was a cap put on the blowout preventer after a couple days to kind of cut it off. And what they did was there was a riser on that cap, and so they started drawing oil and gases up to the surface again. At first they were drawing up about 10,000 barrels per day. Ultimately, before they took that cap off, it got up to about 25,000, so it started giving a lower bound. Unfortunately, with that cap, and you can see because of the way the riser was cut off, it didn't fit very well, and so there was a strong flow coming out the sides or the skirts. The issue was, could that be estimated? And we finally got some better videos of the kink in the riser. As I said, there was appreciable amount coming out of that as well. Now, what happened was that this was the 13th. Our team finally met together, not in a teleconference, but met on Sunday, June 13th. To make the best estimate possible, because what was happening was that on the next Tuesday, Obama was going to give an address to the nation. You probably remember an evening address, and they just wanted the best estimate they could to have in place before he made the address. So we met there to do that, and I put in this graduation ceremony just to show you, our academic quarter was just moving along, and Alberto had to rush over to the graduation because one of his students was graduating and rushed back to the meeting and stuff. And so we met and had pretty lengthy debates and wound up the estimate at the time, again, without good information on a lot of issues that we could talk about in depth. We said it's probably between 20 and 40 with big air bounds on it. Here's our plume team that we took a picture at the NOAA lab, and here's Oscar Flores, a postdoc working with us, and Alberto, Steve Worley, and here's Bill Lair, the person at NOAA, and this is Marcia, and then some of the other members. So anyway, we sent that report in and essentially to Steve Chu. Marcia sent it on to Steve. And so then on the 14th, which I think was a Monday, Steve Chu held a big, I should say, by the way, about our colleagues. So the only person that's not in this is Juan Lazarus, a fellow from UCSD, and his school was out, and he was kind of called to Madrid to be in some review panel, I think. And so he called into the meeting in the middle of the night in Madrid, and he was on the phone the whole time, which amazed me. So anyway, we sent it to Steve Chu, and there was even a bigger teleconference, and there was a lot of people from the government. Ken Salazar was also there, who's the Secretary of the Interior. Marcia was there. There were several people from the White House. And now there were some people from DOE labs, because what they had done was when they put the cap on, they put some pressure probes in it to try to estimate the flow out that was coming out of the sides of this kind of ill-fit cap. It was called a top hat at that time. And so DOE came in with some estimates as well that turned out to be really high, but unfortunately it turned out that the pressure devices weren't working. So, but they got into the estimates, and I think that was very important. So they introduced their own estimates, but after, again, in this meeting that Steve Chu held, after, again, a lot of discussion of the different methodologies, and there was also some estimates from Woods Hole, we came down to this number of 35 to 60,000, which kind of is what's held up now. And again, every time something like this happened, then the press is calling and wanting to know about it and what we think about it and what happened at the meeting and all this kind of stuff. So a lot of press attention, which is not stuff that we're used to as academics. So anyway, so then we pretty much were completing the work. So we introduced a draft report on the 21st with a lot of details in it. And we had two different estimates. One, when we took the riser, flow out of the riser X and the kinks together, added those together, and then the other is when we dealt with after the riser had been cut off. And this was reviewed by some people in the universities and government labs, kind of amended, and a final version was put in. And then the oil was stopped on July 15th. Now, what DOE did in stopping it was that they put a well-fit cap on, and they also put pressure devices in that did work. And so with that, they could make an independent estimate as well of what the flow rate was. So there's really the DOE estimate based upon those pressure probes and then what we're doing. And kind of the final thing was that on Saturday and Sunday, July 31st, August 1st, there was two teleconferences, and Alberto and Steve Worley represented our plume team. And there was a number of people from DOE labs and probably some others there as well. And this final estimate ultimately came out of about 4.9 million barrels of oil over that period of time had gone into the Gulf. And if you multiply that by 42, it's something like 200 million gallons. So that was a number estimated and that people can work with then. So I think this is the time that Alberto takes over.
What I'm going to do now is, Jim has sent kind of the background and all the timeline of this. I'm going to go into a little bit more detail into the technical work that we did, what kind of calculations that we did, based on what information, and our previous experience. So being fluid mechanicians, as Jim mentioned, we're not used to press attention. In fact, we're not even used to having our own students' attention for much longer. Fluid mechanics is a fairly arcane science that finds its uses pretty much everywhere around, but it's mostly ignored. It's one of these things that because it works well, nobody notices. Except in this case, it didn't work quite so well. This is a situation where two scientists with absolutely no previous experience in the oil industry got sucked into the whirlwind of doing this calculation that for the longest time, BP kept saying, no, you can't do this. It can't be done. No. Sorry, these videos are just for the press. So we beg to defer. And the whole thing was done here in Seattle, and it's interesting because a lot of people kept asking us, so are you going down to the Gulf? Are you going to one of these control ships? Or it's really puzzling because from our point of view, there's absolutely no reason. I mean, this thing is happening a mile underwater. We could be sitting on a boat in the Gulf. We'll be getting the video exactly in our computers, exactly the same thing we can do here in Seattle. So that's one of the nice things about technology. But it's no substitute for science. So for my personal involvement in this is very simple. I walk into my office on May 13th, and Jim walked by and said, Alberto, I just got a phone call from a fellow from NOAA who wants to know if we can do some estimates of the flow rate in the Gulf. You must have read about it in the news. And I said, sure, yeah. so what kind of information do we have? Oh, they have some video. Oh, okay, I work with videos all the time. Let's look at it. So he forwards me this email, and there's a link to a YouTube page. And I said, there's no attachment here. I was expecting 100 of megabytes of information, and I get this link to YouTube, and I watch it, and it's really interesting, but I don't do science with YouTube. Well, surprisingly, it's a big wall, so there's always someone who thinks they can do that. So anyhow, somebody pulled it out of YouTube and did some quick calculation, and went to, or rather, NPR went to him, and came out with this 70,000 oils per day. And so suddenly, this became a national issue. Press was all over it. The government was suddenly feeling a lot of pressure, and so on and so forth. And so it kind of trickled down through the levels of government and onto our backs. So suddenly, this was a matter of national urgency, and we had to drop everything we were doing and start calculating. And really, if you get down to it, it's really simple. To calculate a flow rate, this is about the hardest equation that I'm going to have in my slides, so don't worry. It's really, really simple. To calculate a flow rate is just a velocity times an area. And if you want to make it fancy, you can have all these integrals. But really, it's very simple. Because the flow rate that you are calculating is two-phase. It has oil and gas. And for the most part, people don't care about the gas. You don't see it, so it's out of sight, out of mind. People care about the oil, which is the black, oily, thick stuff that gets attached to the rocks and the birds and so on and so forth. So what you really want to calculate is the flow rate of oil, which is the total times some mass fraction, right? So you take a certain percentage of the total flow, say 40%, and that's the barrels of oil that we get in the news. So really, there's not too much about it. We have a technique in the lab that we use all the time. It's actually made the transition from the research lab into industry, and so this is used all the time by car manufacturers, aircraft manufacturers, medical device manufacturers, which is called particle image velocimetry. And the idea, not surprisingly, is to calculate velocity from images of particles. So how do we do that? Well, if you take two images, and these are just idealized images, if you take two images of the flow, you take a transparent fluid, and seed it with particles that are very good light scatterers, so particles that reflect light very well. And then you illuminate the flow in some way, and typically you use a laser plane. What you're going to get is that because the fluid is transparent, it doesn't scatter any light, and so your camera doesn't see anything, so it's black. And then the particles, which are very good, very shiny, very reflective, they scatter all this light, and it is captured by the camera in the form of these dots. And if you take two images at a certain small time apart from each other, you can look at the displacement of these particles in the fluid and calculate the velocity. If you want to do it really, really careful, you don't look at just the displacement of one individual particle, because there may be a lot of error there. You may make a mistake identifying which particle this, in the second image, this original particle is, for example. You do it statistically. So you take a sub-window, which we call the window, the interrogation window, in the original image, and then you take same size windows and essentially move around the second image. And you're looking for a box that matches, in the second image, that matches the first image. And if you find that, then you have your displacement, and from the displacement, you can calculate the velocity. So obviously, we don't do this by hand. We don't sit there looking at the screen, looking at the dots. It would be very time-consuming and painful for our eyesight. When you take a picture with your digital camera, you store the picture in your memory stick, right? And then you take the memory stick, put it in the computer, and do all kinds of things with it. That's because the sensor in the digital camera is converting the light into essentially ones and zeros, into numbers that represents the light intensity at each specific pixel. So if you take this image and you look at the information stored in this image, can be stored as a big table, as a bit matrix of numbers, where each of the numbers represents the light intensity in one of these pixels captured by the camera. So we now have these two images that correspond to a big table of numbers. We can take this table, essentially multiply it by this one, and add all the resulting numbers. It's very, very simple calculations, multiplying and adding. That's something that computers are really good at, and they can do it very fast. So you can essentially take a specific window in the first image, and then take all the possible windows of the same size that are displaced around by a certain displacement, and then calculate that one number that gives you the correlation, the multiplication between the original table of numbers and the resulting, the second table. And that correlation shows up here. You get some smooth function of the correlation. If you look at it from the top, so this is a 3D representation of the value, you look at it from the top, you see that it has a very clear maximum. That maximum gives you the statistical displacement of that box, and therefore, the best estimate of how much this fluid in this window has moved over a certain, over the course of a certain period of time. So you have your, in 2 dimensions, your dx and dy. If you divide it by delta t, well, that's exactly the definition of velocity, right? It's how far something has moved over a certain amount of time. So this is really what we do, and I like to think that we've gotten pretty good at it. But we don't really get this quality video in the lab. At least, you know, you don't get very far in the academic community if you do this. So anyway, this is a real sample. It is not blurred for your pleasure, viewing pleasure. This is a real thing that we got originally from BP. And there's an interesting anecdote, and it's the first time we look at it. This video is actually fairly good quality. If you can't read it, and neither can I, but I've spent a lot of hours looking at it, so now I know what this is. This is an Windows Internet Explorer bar, because the reason why this video is so poor quality is because this is being streamed online and then screen captured on the receiver's computer, and then made into a movie and sent it to us. And we just kept scratching our heads saying, I mean, even if you're videotaping your kid's soccer game, you don't do this. Why would anybody? And there is a reason for it. These videos were being streamed from the boat the ship that was operating the remote operating vehicles on site. They were being streamed through satellite to the office in BP in Houston. And obviously, when you stream things over satellite, you have a very narrow broadband. You don't have a lot of capacity of sending information. So the videos were really being kind of downgraded to send them over. And the reality is that they never thought this was going to be used for any science or any engineering of any kind. They just thought that somebody in Houston, some higher up in Houston, wanted to see what it looked like. And so he had this streaming in his computer. And in fact, some of the videos that we got, you can see the guy actually moving the mouse and minimizing this, and then you see the person's desktop, and then they start opening Word and whatnot. It's really fascinating. So this is roughly what we had in that first week, where we got called into action and everything. There was a lot of motion and a lot of excitement, and they wanted a number by a Monday. And these are the videos that we had that Thursday. So on Saturday morning, very early in the morning, we had another conference call, and before that, somebody actually came on Friday, came on the news and have an update of even a worst case scenario. And then again, the press went into overdrive, and obviously everybody felt the pressure of trying to come up with some reasonable estimates. So finally, we got something like this, which is a lot better video. It's still fairly poor quality. I mean, it shows up pretty well here. But if you look at it in your computer screen, you see that this is fairly old-fashioned kind of low-resolution video, kind of what you're used to with your VHS, not even DVD quality. But this is something that we could work with. This is reasonable. This is another video. The previous one, by the way, is this kink area where this is a 21-inch pipe that was folded over itself, and obviously it's a steel pipe, but over the weight of under the weight of itself, it just crumbles, and there's all these holes where the gas-oil mixture is coming out very fast. This is the other region. This is the end of the riser. So that same pipe that comes out of the blowout preventer falls over, kinks over itself, and then loops for about 5,000 feet of a steel tubing, and then there's at one point on the bottom of the Gulf, there is this end that is gulping out oil and gas. And this is an interesting movie because you see at one point all the stuff that is coming out is very black, very thick black. And you can see that it's coming out fairly horizontally. It's coming out, the density of oil is not all that different from water, so it's coming out almost horizontally through the pipe. And then you see suddenly a gasp of gas, fairly wide bubbles, that come out and they immediately rise to the surface because obviously the density of gas is so much smaller than water. So that was one of the main problems that we had, is that this is by no means an homogeneous, steady flow of fluid. This is really a very dynamic, constantly changing mixture of gas, oil, and some seawater. This is another movie that it's a close-up, and this is one of the ones that we actually use to make the videos. And then you see this lamprey, this poor creature, just being sucked into the gusher and never to be seen again. So there's still life down there. Not a whole lot, but some. So this is the first set of measurements that we took from those videos. And what you see here is just the area of interest. And you see these really little red vectors that are pointing out. And so we take all these vectors, we integrate them over the cross-sectional area, and we get a flow rate. This is the secondary. This is the secondary area. We have a very small hole here that this gushing oil, a mixture of oil and gas. And we have to make some approximations to get what the flow rate is, because we can't really measure down here. It's just too small. It's only maybe 8 pixels across in the hole, and the speeds are way too fast. So we have to go down and make some approximations and use some turbulence theory that we always like to think that it has some use out there, and it actually does. So it's always encouraging. Now, there is a second. So we've gone over how we measure the velocity. But you have to remember, there is still 2 other things that we have to measure. One of them is the gas-oil ratio. So, and this was an area of a lot of controversy, because this is a quantity that, depending on who you talk to, it means completely different things. And so a lot of people in the oil industry who had been working with this had a completely different view of what we needed. And we kept repeating, no, that's fine, but that's not what we need. Because they do a lot of studies when they drill these wells. They do a lot of studies of the thermodynamics and the composition of the gas-oil mixture. But they do them under very different conditions from the flow that was coming out. They essentially take a little sample and they rise it to the surface at constant temperature and constant pressure, and then they do different things. And that's all fine for what they want to do, which is determine what is the composition and what are the thermodynamic properties, so that they can determine what's the best process to follow with that oil when they get it out of the land and to the refinery. But it's really of little use in this estimate. So we have to come up with a way of estimating this quantity from information that was available from BP, but that was not really being used before. And we realized that there's this arcane unit thing that the BP was actually reporting, but without really linking it to the Voigt fraction, which is that for every barrel of oil liquid at the surface, they were collecting 3,000 square feet. Did I say that? No. It's a standard cubic feet. That's what SCF means. As I said, I'm a big fan of international units. A standard cubic feet is not my cup of tea. So anyway, so we had from that information the actual the actual ratio of gas to oil at the surface at the conditions that this mixture was flowing. Apparently, from before the explosion, the number was reported to be 3,000, which turns out to be a volume fraction of 0.25. So 25% of the volume that we were measuring out of that pipe was liquid oil, and 75% was gas, which has a lower, if you want, signature or a lower ranking in the importance of this oil spill. Towards the end of our work, the oil that was collected at the surface after the caps were put on and everything was finally coming together, the numbers actually had changed, and they were collecting 2,200 standard cubic feet of oil per barrel of gas per barrel of oil, which turns out to be more like 41%. So that's a 50% variation right there. There's a lot of uncertainty in all of these numbers, and it took about a month to go from this number to this number as more and more information came together. So obviously the estimates got refined quite a bit. And finally, if you're still following me, I said we needed three numbers: a velocity, gas to oil ratio, and then an area. And the area is really something that was given by the sonar surveys from BP. There was this crumbling of the riser and this internal obstruction by the drill pipe and so on and so forth. So this is really the information that we had to work with. So finally, we get to some numbers. With all this information, about 10 days, let's say, 10 days after we actually got our hands on a decent video and we started to iron out all the details, we came out with this estimate of 16,000 to 28,000 barrels per day, based on the information that we had. And this is very important to keep in mind. All the information that we had up to this point had been provided by BP. It was all videos that were taken by the aerobase by BP. It was gas to oil ratio provided from samples taken before the accident by BP, and it was the cross-sectional area that was supplied to us by BP. And so when we came out with our estimate, we make it very clear that what we were measuring was an absolute minimum. This was based on about maybe 30 seconds of video. Out of the oil had been spilling at that point for about 40 to 45 days. We had about a 30-second clip of video of not all that high quality. So we made it very clear that the numbers that we're measuring were an absolute minimum. There's absolutely no way less than this is coming out. It could be more, most likely. How much more? We don't know. So we'd rather just give an absolute minimum. So of course, that all got complicated with other estimates from other groups and the press and so on and so forth. And so it got converted into this 12 to 19,000 that Jim just mentioned. At the time, they had placed this riser insertion tube tool, which was sucking out a little bit of oil from the end of the riser, and they realized this was not going to have any significant impact. It could collect at most maybe 5,000 barrels. And so they removed that and they started the effort for top kill. So before doing the top kill, BP had to take the riser and cut it right above the BOP. And ideally, it had been a very clean cut, and then something, a cap with a very good fitting could have been put in. But unfortunately, that didn't quite work so well. This is the geometry that you've just seen of what the resulting riser. So this is the joint right on top of the BOP, the last flange, and then this is the beginning of the riser, what got mangled pretty badly there. As a result of that, this is the flow coming out. So this video is actually high-resolution video. This is what you get if you rent a movie on Blu-ray. So this is for the first time we had something that we would consider possible in our laboratory experiments. It's not quite the top of the line, but is something acceptable as a scientific instrument. One of the differences that you see is that the oil and gas here is a lot more mixed. In the riser, you see very clear difference between the oil and the gas because the oil and gas is flowing over a course of about a mile of a horizontal pipe, so you have plenty of time to segregate before it comes out of the end. Here it's just coming out of the BOP in a vertical configuration, so it's coming out very, very fast and well mixed. And even there, you can see there's two clear grades of brown depending on how much oil and gas is in there. And that has to do with the fact that there's oil through one of the drilling pipes that is in there, about an 8-inch pipe in there. It has a different composition from what is coming out through the rest. So with this type of video, we can get really detailed information. And what I'm showing here is velocity. Red is high velocities, blue is slow. So you can see the structure of the velocity field from these images, from the particle image velocimetry. And then if you take lines like this, you see the velocity profiles marked here, and they are slightly different. So for the first time, we get a really good estimate of the velocity. Now, there is a little new piece of uncertainty that comes into this, and it's the fact that in the laboratory, when we use these techniques, we have complete control over the flow. So we seed the flow with these particles that we choose. And the fluid, the background fluid, is typically transparent. So we really see inside. We see what's going through the core of that pipe. Here, we're only seeing the surface. It's a completely opaque jet. So what we are measuring here is this velocity of this outer surface of the jet that is kind of convoluted and is billowing out of the pipe. Whereas really what we need to measure the flow rate is this velocity of the core. Because right at the outlet of the pipe, we have this almost uniform velocity that we can estimate the flow rate by just the velocity of the core times the area of the pipe. But we're not measuring this, we're measuring this. So there is a whole lot of different theories that we can use to relate those two numbers. There is a lot of information in the literature that we could borrow from that tells us that for a jet of a certain fluid, let's say water, coming out in a stagnant environment of the same fluid, that ratio is about 1.6. But we don't have that. We have a mixture of gas and oil coming out in the presence of seawater. And so it's a very, very complicated process where you have mixing going on. You have the fact that the fluid coming out is lighter, so it's going to be accelerated by buoyancy. So there's a lot of secondary effects that when they combine together, they can have a pretty significant effect. So we chose to use this classical number from the literature and then modify it by the effect of the density difference between the seawater and the fluid coming out of the spill, which is a mixture of oil and gas. So with all these complicated theories put on top of the measurements, we got a best estimate of about 38,000 barrels per day with a range possibly from using different hypotheses or looking at different videos of between 22 and 54,000 barrels per day. Now, we are one of the groups working on this. There's other groups working for the Department of the Interior and for the Department of Energy. So we all had a big powwow together on June 14th, as Jim has mentioned, where we were supposed to iron out all of the different measurements. So what other things were people doing? Well, there was a group from the Woods Hole Institute of Oceanography where they took a standard sonar measurements that are used in oceanography, in field oceanography commonly, and they mounted them on one of the ROVs that BP was operating out of their site. And essentially what they did is the ADCP is a system that measures the velocity of the water. And then the imaging sonar essentially looks across and looks at where is the perimeter of the gas-oil mixture and what is outside, which is water. And so again, you have a velocity and an area. You multiply that together, and you have flow rate. Unfortunately, there's a lot of assumptions because these two instruments can't measure in the same point. And so you have a cross-sectional area in one place and a velocity at a completely different place. And you have to bring them together and kind of fudge them together. And so there's a lot of assumptions that go in there that and raise the uncertainty. And the other thing is, again, you have the problem of the oil to gas ratio, which you haven't measured there. So there's again a lot of uncertainty. The other technique that the Department of Energy used was they put some pressure measurements inside this cap. This is the first cap that was tried. This is the one that was used to collect oil at the surface for about a month. They went from collecting a few thousand to at the top of collection about 25,000, and there was still some oil leaking out. And then eventually they remove it, and they put the sealing cap, the one that finally closed the flow. But that was about a month later. So they had put some pressure measurements in here. And so if you're a mechanical engineering and you have a flow system where you know pressures, sure, I can measure the flow. This is something that we teach in junior year fluid mechanics all the time. A lot of our students go into HVAC, calculating air conditioning for buildings, and this is essentially their bread and butter. I mean, they do this all the time. Unfortunately, this is not a simple flow of air. What you have in here is a mixture of oil and gas. And the other thing is you have pretty good control over what this geometry is because you've manufactured it. You have very poor information about what this geometry is because this is essentially a leak. If you knew what it was, then you'd have made the cap so that it didn't leak. So if you really want to do a quick and dirty calculation, you convert this into an electrical analog where you have pressure for the voltage. So you have a voltage difference, a pressure difference. That drives a flow. That's in the electrical analog, that would be the electrical intensity. And then you have a hydraulic resistance for each of these three flow paths, which is a resistance, right? You know the resistance and you know the pressures, you can calculate these Qs. Unfortunately, as I said, R1 is fairly well known because this is a tube that you have manufactured. Flow 2 is a vent that you also have manufactured, and you can test in the surface and get some estimates. But R3 is the hydraulic resistance over this very complicated geometry of the leak. And so obviously that's going to impact the calculations quite a bit. So again, another reasonable thing to try, but has its own set of problems. So we all hash out all the numbers together, and after quite a bit of back and forth, we came out with this estimate of 35,000 to 60,000. And the idea behind this was helping the response. The question that was present at the time was, BP was going to start capturing the oil on the surface, and they needed to know how much oil was going to be collected to mobilize the capturing ships and then the tankers to bring it back to shore. And so the question was, well, do we need 2 risers or 3 risers? Do we need 2 tankers or 5 tankers? So that was kind of the rationale for this. And obviously, there's always a safety margin where you want to err on the safe side. But you want to know what kind of numbers you are working with. So that was the goal of this. Just to finish the story, although our involvement after that point started to decay, we started to go into more writing reports, documenting everything that we had done. Once the sealing cap was put on July 15th, the oil stopped coming, and so we're really out of business because there was no more oil flow to measure. But we did have a last conference call where the goal was to produce a final estimate. And since our measurements had been so instrumental throughout this period of about 6 weeks in estimating the flow at each step, before the other groups could kind of catch up and start doing all the calculations based on the reservoir and the actual flow inside the well and the integrity of the well and so on and so forth, we were asked to participate in this. Eventually, the final flow rate was estimated at 53,000 barrels per day, and this was based on some measurements that were made on July 15th, the day that the sealing cap was put on. So the moment that you're going to start to close, you put this sealing cap, there's no leakage through the bottom, and you're going to start to close the valves and record the pressure there as you close the valve, then you have a fully engineered problem where you know all the parameters, and then you can go and calculate things finally. And of course, that was the day that they closed the oil. So they could have done that before, then no need to measure the flow. And so eventually, if you take that number and multiply it, estimate a little bit of a decay over time because of the reservoir depletion, the fact that the oil is coming out, the pressure in the reservoir is going down slightly over time. They finally estimated that over the 87 days of the spill, there were 4.9 million barrels that came out. So that's it's kind of the corollary to our work there. And that's all we have to say. We'll take questions.
So we really want to thank Professors Riley and Aliseda for that very interesting presentation. And now you have the answer to the mystery of where on earth was all that data coming from that we were hearing on NPR, and now we know. So we're walking up the side aisles to pick up your questions. If you could pass them in, that would be great. And I'm going to start by asking a question of both of you. And maybe if you could both come up, that would be great. So there's always wonderful opportunities. Come on over here so we can get you in the camera. Oh, yeah. Always wonderful opportunities to learn things, lessons learned from these exercises to share with others. So I'm curious whether you're going to be producing some sort of a paper on the lessons you learned so that people can learn from this for the future.
I mean, we have discussed whether we should write up, how to make a measurement like this. And in fact, talked to some funding agencies about it. We're not sure where it's going to go yet.
Yeah, so in my view, the main lesson that we learn on this is that we need to do more work in advance of this happening again. Yeah. Mm-hmm. And we need to have good techniques and good information in advance so that when this happens again, it doesn't create this havoc.
Yeah, so no techniques existed at the time.
Right.
So there's some recommendations perhaps that could come out to agencies such as Department of Energy or Interior in terms of how to at least know what's going on a little bit better next time.
Yeah, that's the main.
Besides an upgrade to YouTube.
Yeah.
Okay, it looks like there's quite a few questions here. This one, did BP scientists really not have the ability to perform their own calculations? If not, did they ever contact you to learn how?
We can't really speculate on what the BP scientists were doing. Our perception in working with BP was that their emphasis was really on understanding what was happening at the well in terms of how to close it. They never placed an emphasis on measuring the flow rate. And this is, of course, a decision that is taken at the management level, not at the technical level. Sure. So even if they had the technical capability, under a condition of a lot of pressure and a lot of diverging interest, the resources were allocated in one direction and maybe not in another. Okay. We were never contacted. I mean, at the same time, we were never contacted because by the time we got in touch with BP, we were already doing it. So there was maybe not so much interest in doing it twice.
Yeah, we have two colleagues in Cambridge, in England, where BP has a lab. And we have the feeling that they probably made some estimates, and we'll see them, at least one of them, in November and find out. Mm-hmm. Yeah.
Great. Okay, well, this kind of relates. It says, would it be possible to build a physical model of the pipe openings and leaks and actually measure the flow?
You could potentially do a physical model of this in the laboratory. What you are not going to be able to replicate is the pressure differences between the reservoir and the oil well, just because the numbers are so fantastically astronomical. You have 12,000 psi pressure difference between that, and you can generate 10,000 PSIs in the lab in a small container under very controlled conditions, but you can't have a big tank with thousands of barrels at that pressure and then gushing it out. It's just It would be a
Be exciting.
yeah, it would be a major undertaking. Yeah.
Why couldn't velocity measurement devices be introduced across the plume to estimate the velocity profile?
That was something that came up all the time. There was actually scientists in our group that were suggesting to do that. The main reason why that can not be done, or why it would be extremely difficult, is that the moment that you put anything in the flow, you stop you're generating an area where the gas and the oil get stagnant, and the gas at that pressure and temperature immediately forms hydrates. So it forms these solid crystals that attach to the probe and clog it immediately. In fact, there were several efforts to close the flow that were hindered by the hydrates.
Mm-hmm.
Well, here is a very basic question about reservoir engineering, and that is, what causes the pressure?
Well, just the earth, really.
Yeah,
you essentially have
overburden.
We have all the
Yes,
ocean
miles
on
of
top
earth.
of you pressing down. So.
Okay. Let's see. You mentioned that your estimates were revised downwards a number of times. How comfortable are you with the final estimates of oil flow? So the total number you came up with.
I didn't say that our estimates were revised downwards. I'd say that we always gave a range that we felt comfortable with, and then what was reported in the press was some number that caught somebody's attention. But just by the nature of things, it's a lot easier to fix your attention in one number than on a range. It's a lot less newsworthy, I think. But that we never felt that our estimates were being downgraded.
Okay. Quick question, I'm not sure you'll know the answer to this, but do you know how much oil was recovered by BP with the tanker ships?
It was about 800,000 to 900,000 barrels. So about a little bit less than 20% of what came out.
Yeah, there was a group that's studied that, and they tried to estimate all of the sources, how much was burned off, how much evaporated, how much was drawn to the ship. And so they have some good numbers on that, but not how much is below the surface.
Okay.
Yeah.
It's an interesting question. Was any information from relief drilling used in the later flow rate estimates? Were they able to get any data from actually that relief well that helped you revise your estimates?
Not that we know of.
No, not that we know of. But by the time the relief well intercepted the Deepwater Horizon well, it had already been cemented from the top, and so.
Yeah. So they killed it immediately.
Yeah, I can't think of any information that have come out of that.
Okay, did cutting the riser increase the flow, and if so, how much? Yes, by a bunch.
It increased the flow, certainly. The matter of how much is a matter of controversy. But no, it wasn't by much. Yeah. Most of the estimates were in a range between 5 and 20%. And if you take into account that it only took a couple of days after they cut the riser to put that sealing cap and start flowing oil to the surface to a ship, that probably more than compensated what the increase because of the cut.
Okay, this question here, I think I know the answer to this, but were particles injected through the blowout preventer to get better imaging?
No.
Didn't think so.
That was
probably not a priority.
Yeah. That was impossible.
Okay. What after interacting with oil companies this summer, do you think the direction should be on the part of the oil or energy industry? And I think it probably gets to, what can they learn from this from your perspectives, recognizing you're not oil and gas folks that might help mitigate the situation in the future? It sort of relates to my first question. Yeah.
So
what can they learn? Yeah.
I mean, we didn't have much. We had almost no interaction directly with oil companies.
I would say develop the techniques in the laboratory so that they are ready when you have to apply them in the field, and you don't have to start improvising at 5,000 feet depth.
Right. Yeah, these imaging techniques could be developed so they're much more accurate with some experiments.
Okay. Just a couple more here. SAS, has the flow been stopped completely? And I think we know that
Yes.
it
Yeah.
has, in fact. This one, how do you identify the particles in the flow?
In the laboratory technique, the particles are identified because they reflect the light that you shine on them. The fluid is transparent, so you don't get any reflection. If you then put the particles, you take a picture, it would essentially be all black. Because you're illuminating on a plane that is perpendicular to the direction where you're taking the picture. So essentially, no light, the light would just go through and you'd never see it. For this experiment, what you're seeing is you're illuminating from the back, kind of like what they are doing right now from the TV. They're illuminating and they are capturing the light that is reflected off of us. It's the same thing where in those pictures, the ROV is illuminating the surface of the jet, and what we are seeing in the camera is the light reflected from the surface of the jet back into the camera.
Okay. There are a few more questions up here that I haven't asked because I know that they actually don't relate specifically to the topic these gentlemen are well versed in around fluid flow, but I would encourage you, or I couldn't read them, I'd encourage you to come up if you would like to ask them later, and we'll see if they can interpret them better. But please join me in thanking Professors Riley and Aliseda for a great presentation.